In Lecture 8, we're going to continue talking about uniform minimum variance unbiased estimators. We mentioned these at the end of lecture last time, and for the next, say, lecture or two, or maybe 3 or 4, we're going to talk about finding the kind of best estimators. And this is one of the kind of core topics of this course. Of course, we want to talk about estimation. We're going to talk about how do we kind of estimate things as best as possible. And this was theory that was developed in, say, 30s, 40s, 50s, a lot of it in the past century. So relatively modern as far as mathematics goes, right? This isn't calculus, which was developed, in the 16th century. Okay, so last time we ended with our definition. And our definition was of a uniform, or uniformly, minimum variance, unbiased estimator. And this is really quite a mouthful. And so what everyone calls this is the UMVUE. Occasionally people will leave off the U and just call it the minimum variance unbiased estimator. But we call some estimator, let's say T, or what did we use last time? We can call it maybe theta hat star. So here star is going to mean it's the best estimator. And we call theta hat star the UMVUE if it basically is a minimum variance unbiased estimator. And here we're estimating some quantity. So generally, that quantity could be a function of a parameter. Maybe we don't want to estimate theta directly. Maybe we want to estimate theta squared, or square root of theta, or log of theta, right? So maybe, for example, theta might be our mean. We might not want to estimate just the mean directly. We might want to estimate some function of it. So tau here is just some function, some real bad function one like we're used to. And so we call theta hat the UMVUE of whatever function we want. Tau could just be the identity function, so it could be theta, but it could be another function. We call it the UMVUE of tau theta if we have two conditions that are satisfied. One, it better be unbiased. So we'll take these in kind of reversed order. The UMVUE is an unbiased estimator. So it's unbiased, which means that the expected value of my optimal estimator, let's call it theta hat star, is going to be whatever tau of theta is, be it squared, square root, log, whatever fun function you want to apply there. Cool. And the second condition, so it's unbiased, it also needs to be minimum variance. So not too hard to remember. So minimum variance. And this condition, we can say, is that the variance of our best estimator, theta hat star, is no greater than the variance of any other estimator, of any other unbiased estimator, theta hat. And this is going to be true for any other unbiased estimator, theta hat, of the same function. Let's say tau of theta. Okay. So the condition here is that this has to be true for all possible theta. We could say for all theta in our space of possible, our parameter space, capital theta. So we could even denote here that the variance, these variances very likely depend on what the true parameter theta is. But it doesn't matter what the truth is, what theta actually is. We want this thing to be the best estimator in all cases. The reason being is that we don't know what the truth is, right? If we knew what the truth is, we wouldn't have to solve the problem. We wouldn't have to estimate it. We don't know what the truth is. And so, if possible, we would like our best estimator to be the best regardless of the truth is, so we can always be assured that no matter what the truth is, this is going to be the best thing to do. Now, I've written this in terms of variance, saying it's a minimum variance. We noted last time that if unbiased, then the MSE is the same thing as the variance, right? And so you could talk about this in terms of mean squared error. If you remember, the MSE is the variance plus the squared bias. So it doesn't particularly matter which one we talk about for the unbiased case. So that's one thing that makes it like nice using an unbiased estimator. It's certainly not true that it's always the best. So one reason we want to talk about unbiased estimators is, well, it's actually nice because the MSE is just the variance. So that's easy to talk about. The other reason is that it restricts our class of possible estimators to something that is reasonable. And under which we can actually get a best estimator, a UMVUE. So we want this estimator to be the best for all possible theta, right? So here is maybe my space of possible thetas. And it's possible that, for different values of the true parameter, I'm going to get a different MSE, different variance, different, right? And so it's possible that, like, that I can draw this curve is, say, the MSE of what purported is my best estimator, right? And if this thing is truly the best estimator, and then if I look at, say, the MSE function of the variance for some other estimator, call it theta hat, so this is the MSE of some other estimator theta hat, it would have to be above. For any value of theta you choose, right, the MSE of that other estimator is above, lies above the MSE of our best one. Right, so that's what it means to be, this is what the second condition means. It's minimum variance across all possible values of theta. Now, if we didn't look at just unbiased estimators, or in some way restrict the set of estimators, if we just allowed everything, it would be very easy to say that if, for instance, this is where theta is equal to 5 at this point, if I looked at some estimator, some statistic, let's call it t, you could look at, say, the MSE. If my statistic, my estimator, maybe I'm going to estimate it with this statistic t, with the estimator t, that is always 5, right? So it doesn't matter what my data is. We talked about this last time. This is kind of a degenerate, kind of silly estimator. It's silly in some ways because it's not unbiased. It's not the whole story, but it's part of what's going on. And if I allowed such a silly estimator that didn't actually use the data but always predicted 5, when theta was actually 5, it would have exactly a 0 MSE. So this would be the MSE of t is 0 when I just happen to come across the fact that theta is actually 5, for example. And so this would be an estimator that at some point has a lower MSE than my best estimator. So this is kind of a proof by contradiction that if I allowed this kind of degenerate, silly estimator, you wouldn't ever be able to find the best estimator, because you could always, whatever one you propose, whatever theta hat star you proposed, you could always just come up with one that was silly, and there'd be some point where it beats theta hat star. We don't want there to be any point where it beats theta hat star. And so what we do is we basically say not allowed. We don't allow these estimators. We're going to restrict the class of estimators we look at to not allow these, and that's going to allow us to actually find, in some cases, a best estimator. And the way we do it in particular is this first point, is we make it unbiased. That sufficiently restricts the class of estimators that allows the theory to go through and us to prove that there is actually a minimum variance estimator. And as we saw, you couldn't generally do this. Okay. That's not to say that unbiasedness is the be-all, end-all of everything. Some cases, if you have a small bias, but a much, much smaller variance, you actually do better than working with an unbiased estimator in terms of, say, MSE or something like that. So that's kind of a place where the theory breaks down a little bit, at least in this course. There are more advanced ways you could talk about it. You could limit the bias to a certain extent, but yeah, so that's kind of the motivation for working with unbiased. I don't want people coming at this course thinking if it's not unbiased, it's not worth it. No, there are very many bias estimators that are great to work with. It's just you can't prove that in every possible case they are going to be the best. But it might be that you could argue in sufficiently a number of cases they are, and the ones you're going to see they are, and that kind of thing. So you could, in a kind of second course in this, you could develop the theory further. Okay, so let's kind of start down the road on how to find these minimum variance unbiased estimators, these UMVUEs. So the way we're going to do this is we're first going to talk about what's called the score. And we're going to be doing some kind of weird things here. So it's going to be important to keep in mind that, right, when I write this blackboard bold X with this double hash here, this is random. And this, or I guess typically I write it as a lowercase, is not. It's just a vector. In Rn, you can think of x tilde as a random vector, let's say. So we're going to do something a little bit weird, but let's talk about the definition of what score is. It's going to be kind of a central topic in talking about how we can maybe prove that something is the best estimator. So as our setup with all these problems, we're going to assume we have some data. It's from some distribution parameterized by parameter theta. Theta lives in some parameter space, capital theta. This is supposed to read where. Then the score, we're going to call it capital S for score. And it's going to be it's going to be a random variable. So we're going to note that it relies on our random sample, x tilde. And you could even say that it's going to depend on what the true value of theta is, the unknown value of theta. So we'll put a little theta to denote that. And the score is going to be, I'm going to write it this way. It is going to be the derivative of the log likelihood with respect to theta. Now, I'm going to put kind of scare quotes around this because we have to be a bit careful with what I mean here. Basically, what I mean, because we said that the score thing is going to be random. It's going to be a function of our random sample. The likelihood function isn't generally random. but I'm a little bit lazy and I'm going to abuse this notation. What we really mean is that I'm going to take, so my, if I look at the derivative, so this is my log likelihood, right? F of theta is basically the same thing as the likelihood. And you can take a derivative of it with respect to theta. That would give you something that depends on potentially theta and the x's. And I could plug into that thing my random sample. So that's maybe a better way of thinking about it. Is there another way of writing this out even more explicitly? Well, I think it's probably clear enough for now. Let's just talk about it. So why is this different? Normally, when we plug into, say, this function f, we're plugging in some vector, little x tilde. Now I'm basically plugging in my random sample, my random vector. So this is a bit of a kind of switch here. So let me just say, notice the difference, right? Normally we'd look at like f theta of x, right? That is just some number, right? And I'm plugging in my x tilde, which is some vector. Difference between this and f theta is just some function. You could plug the random vector into it, right? It's just some function. You could plug the random vector into it. That's allowable. It's a bit of a strange thing to do, but we do strange things in statistics. And that's exactly what I'm doing here, except instead of plugging it in to, instead of plugging into f theta, I'm basically looking at df theta d theta, this thing, which depends on x, but you could instead plug in the random x. So this is basically like if we take that derivative of a log likelihood, and in all the places that we have the kind of deterministic x, little x of n, we've replaced them with the random capital X of n. Okay, so just keep in mind when we're talking about this that there is a, it's not that important, but you can get confused if you lose track of the fact that this thing is actually random. I'm going to write it as dLd theta throughout here. Context will hopefully make it clear that it is we're kind of considering a random quantity, right? Maybe an example would be really informative here. Let's see if we can come up on the fly with an example here. But let me just back off. That's the score. So the score is just the log likelihood, the derivative of the log likelihood, but then evaluated, instead of my deterministic little x of n's, I plug in my random x of n's, and that's the random now, so random quantity. Let's look at an example. That's probably the clearest way to clear all this up, okay? So what's an easy example? Maybe a Poisson. So let's say I have data. No, that's even easier. Exponential. Let's go with an exponential distribution. Okay? And so it has some parameter lambda, and f lambda of x is lambda e to the negative lambda x. Indicator x is bigger than 0. So the joint distribution of all of these, whoops. Now we're plugging in little x, right? That's the product of my marginals. And it's lambda e to the negative lambda, little x of n's. X of n is bigger than 0. All right, we've done this one a couple times now. So I can pull out this lambda to the n, e to the negative lambda, like that. And we've seen now that you can write this as, let's say the minimum, however we want to write that, is bigger than 0, right? So that's, I'm going to go through that pretty fast, but we've seen that a couple times. Okay. And of course, you could call this the likelihood function of lambda. That's just the joint distribution. So the log likelihood function would be n log lambda minus lambda sum of the x of n's plus log of the indicator xn bigger than 0. We often kind of leave this off because you assume the data is from exponential. The minimum has to always be bigger than 0, and so this is always satisfied. It's always 1, and so the log bit is always 0. So you can always just kind of optionally leave it off, right? And you can always kind of optionally leave off the support as long as it doesn't depend on the parameter. So this doesn't depend on the parameter, so this makes this kind of thing optional. It's not going to affect, in some ways optional, it's not going to affect anything. We're going to drop it. So say if you want to find the MLE, right? And it certainly doesn't depend on the parameter, so I'm going to take a derivative of this thing, which I'm now going to do, dl d lambda. It's going to go away. It doesn't depend on the parameter. What do I get? N over lambda, we've done this a couple times, minus the sum. Okay. So now I've used dl d lambda in this way, right? So the score, so this is, say, what we think of traditionally as the derivative of that log likelihood. I could say the score here, S, is basically, I'm going to take this above formula, n over lambda minus the sum, but instead of my little x's, I'm going to replace them with my capital X of n's, right? And so now that's a random quantity, right? Just replace my little x of n's with my random capital ones, right? It's a random quantity. And I'm going to be lazy because I like this notation, dl d lambda, and I'm going to say this is, quote, dl d lambda. If it matters, we'll distinguish between the two, but it's typically kind of not going to matter. So this should be my score function. It depends on lambda. It's a function of my x's, my random x's, right? So not too bad. It's a little bit strange because we're kind of plugging in x of n's, which are assumed to come from this distribution, into the formula here. Okay, but at the end of the day, I'm going to use this notation, call it dl d theta generally, but that's as complicated as it is. Okay, you do your normal calculation, take a derivative, and plug it in. Okay, so this is actually useful, jumping off, because we see that there's kind of the deterministic, so let's kind of say deterministic, right? In so much as we assume the x of n's are observed, and this is random. Or we assume these capital X of n's are unobserved. They're random variables. Now, for the deterministic version, right, what does, of course, dl d theta tell us? Let me write that out. Let's say, what does tell us? Okay. So let's imagine that we calculate dl d theta over our whole space of possible thetas, capital theta, and we'll plot L of theta, and maybe our log likelihood function, so let's say this is L of theta, right, over my possible values of theta. Maybe this is what it looks like, right? And we don't know what the true value of theta is, but we can observe this deterministic version. And if I were to look at some value, maybe this over here, this is theta 1. In this case, DLD theta would be what would be negative, pointing that way, right? And it basically tells us, so that would be kind of negative DLD theta, right? Well, let's think about it this way, right? So it would be negative in this case. It basically is going to tell us to go backwards, right? So that's how we want to think about it, right? So it would tell us to go that the maximum, right? Our MLE is up here. And so if we're over here at theta 1, if we look at the derivative evaluated at theta 1, it would tell us actually go backwards this way, because our MLE is going to be this way. Alternatively, if we were to look at some point theta 2 over here and look at DLD theta, sorry, this is not negative of it, but this is, it would be negative, so it would be pointing this way. Over here, it's going to be positive, and it's going to tell us to find our MLE, we should move this way. So at the various points, you can think of this gradient or this derivative as pointing us, pushing us towards the maximum, right? Of course, at the maximum, the point at the maximum there, the point that achieves this maximum is called the MLE, and at this maximum, if we looked at the derivative at the maximum, of course that would be 0, right? That's the whole point. When we find our MLE, we take DLD theta and we solve for when it gives us 0. So at the maximum, at the MLE, the log likelihood is going to give us 0. And at the other points, it's going to kind of point us towards that maximum in some way. So if we follow the gradient or follow the derivative at the points, it will push us towards it. So if we're over here and we say, what's DLD theta? Oh, it's negative. Okay, we take some steps up here. Oh, it's negative still. Negative. Take some steps. Negative. Make theta smaller. Negative. Theta smaller. Uh-oh. Maybe we overshot, so we come back and we take, because over here, say it's going to be positive, we'll take some steps. This is called what's called gradient ascent. It's an optimization technique. Point being is the gradient kind of tells us where to go to find the maximum. And at that maximum, as long as this thing is kind of nicely differentiable, it's 0. Okay, so DLD theta is telling us something about where to find this maximum. If we look at the random version, the score, right, which is basically the random version of the derivative of the log likelihood, we have a similar fact. I'll write it as a fact, we can call it a theorem, which is that we can look at the expected value, let's call it the score, well, let's just leave off all the little twiddly bits. S, our score, is random, and this expectation is 0. So that's similar, kind of a similar flavor to what we got here, which is that in the deterministic case, we use the derivative of the log likelihood to find this MLE. The MLE is defined as the point where that derivative is 0 in the differentiable cases. And if we view that thing as a random, if you kind of plug in our random sample into that derivative, we get what's called the score. And the score, on average, is going to be 0. So let's draw a little picture associated with that. So here's our space of possible thetas, capital theta. And maybe our true theta is here, okay? And what we do is we're now going to assume that we take a sample, we look at the likelihood function, right? We look at the derivative of the likelihood function. It's basically like if I were to take a sample, look at the derivative of the likelihood function, what kind of on average is that derivative going to be? So you could imagine what you basically have is like, so I can take one sample here. So maybe this is my first sample. This is L1. Yeah, let's call it S1, right? So this is like one of the kind of samples, and I get my derivative, my score, and maybe it's here, and this would be the maximizing value. You can take another one. Maybe that's the likelihood function. Maybe this is another one. But the point is that kind of on average, how do we want to think about this? Is that kind of on average, right? So what do I want to say? The score here, right? This is on average the maximum value here. Basically, the point is going to, if I look at theta, kind of on average, we'll get different scores depending on exactly. Oh, I should do that in blue, shouldn't I? We'll get different kind of log likelihood functions depending on exactly where we're going to be and under different samples. But on average, if we look at it at this theta value, we're going to find that that this gives us the MLE, right? So the idea being is that if we look at the kind of sample scores for different realizations of our data, on average at the true parameter, that the maximum, they're going to have their maximum at that true parameter, which is to say that you're going to have, on average, kind of you're going to get the MLE to align with that truth. So it's kind of it's a little more complicated of a picture, but it's a similar kind of idea, which is that for a single observation, we define the MLE basically where the score is 0, or where the derivative log likelihood is 0, and the score is kind of is the random version of this. And if we take a bunch of observations and we calculate the score at the true theta, we're going to get 0, which is to say that the true MLE on average is going to be aligning with the true parameter we want to estimate. Okay, so we can actually do a proof of this fact. So the fact is that we want to show that if we look at the score, which depends on theta, on average, or in expectation, this thing is going to be 0. So again, we got to remember that the score thing is random, right? So it has an expectation, has a variance, which we'll talk about. Okay. So the expected value of the score is at theta, right? So we assume the true value is theta, and we're going to look at the score at that true value, right? So that's kind of what we're talking about in this previous picture, right? You can calculate the score at many different values of theta. If you calculate it at the true value of theta, on average, it's going to be 0. So on average, our MLE is going to be correct. We look at this, and what is this? This is just this score function, but now instead of my random x's, I plug in my little x's, right? And we multiply by the PDF, right? I'm taking my expectation against my data. So it's a function, which is s times the PDF, and then we take the derivative. Or I'm sorry, and then we integrate, right? So this is my lazy notation. You might say, how can you integrate against a vector? This is my lazy notation for whatever n integrals, right? dx1, dx2, dxn, right? So I'm just going to write it as dx tilde, which just means this is really multiple integrals, but I don't want to have to write that over and over and over again. Okay. So we noted that there's kind of this deterministic version, which is dl d theta, and then there's kind of this score version, which is basically, we treat it as a random quantity. And so now if I take that thing, but I'm plugging in, this is totally deterministic, right? This is kind of the deterministic. This is exactly dl d theta. No fudging about here, right? This is, we go back up to our definition, except instead of the random, now we have our deterministic. This is just derivative of log of the PDF. So it's dl d theta, and we multiply against f theta of that, and we integrate. So our side here is that dl d theta is dd theta of log f of theta, right? Of our axis, right? That's the definition of L of theta is that. That's the definition of our derivative. So this is, of course, there's a chain rule, so it's going to be the derivative. Our chain rule says this is derivative dd theta of the inner part, f theta of x, over, all right, what's the chain rule for, say, ddx of log u of x? This is u prime of x over u of x. And so this is derivative of the inner part over f theta of x, right? So that's kind of on our side here. So we can plug in dl d theta for this form instead. So this is the integral dd theta f theta of x over f theta of x times f theta of x. Integrate. And so we notice you can cancel those out, right? Those get crossed out. And what we're left with is the integral of the derivative of our PDF. Now, I'm going to make a move here. And this move is only legal in certain circumstances. We're going to say that we have enough, what they're going to call regularity. And by regularity, I mean niceness, to interchange integration and differentiation. So you're not generally allowed to do that. I'm not generally allowed to swap an integral, the order of an integration and a differentiation. If you have what we call enough regularity, which is basically a way of saying the function we're integrating is nice enough, then I could do that. If I could do that, I could instead write this as dd theta of the integral of f theta of x. And now, this is just the integral of a PDF. So integral of a PDF. And we know that the integral of a PDF is always 1. And so what we get is derivative with respect to theta of the number 1, and the derivative of any constant is 0. So this shows that in expectation, the score is 0. It relied on the fact that we had enough regularity or enough niceness to interchange that integration and that differentiation, which is not always true. And so this begs the question of when is this a valid move? And I said kind of vaguely you have to have enough niceness or regularity. So I'll say 1. If we're dealing with an exponential family. So if f is an exponential family, say f theta is some exponential family, this is going to work. So this is really why we care about exponential families. This always works for them. And the subsequent theorems, some of the subsequent theorems we're going to prove, we're going to talk about today, also rely on this fact that we can do this interchange of differentiation and integration, which is true, always acceptable for exponential families. It is not acceptable when the support of f theta depends on theta. So e.g. Uniform 0 to theta, the support of that distribution depends on theta, and so this is not going to be a allowable move. But exponential families, we know definitionally the support cannot depend on the unknown parameter, and more generally, I'm just going to tell you that it's always going to work. So this first theorem is not that super interesting, but it's going to lead us to a really interesting result. But the first fact to know about score is that in expectation, the score is 0. Okay. So let's go back again to our little picture of so what's our picture? A picture of L of theta against theta, right? We said that the picture you should have in your mind is that we have this MLE here, and that basically corresponds to the maximum of our likelihood or our log likelihood, right? And we said that the derivative is basically tells us either if we're not at that maximum, how we move in the theta space back and forth to move this way or to move this way to get to the maximum. And at this maximum, right, kind of definitionally, for as long as our likelihood is differentiable, dl d theta is 0. Okay. So that's the first derivative. What about the second derivative? D squared L d theta squared. So consider two different possibilities. Here are my two possibilities. In my first possibility, here is my MLE, and my likelihood looks kind of like this. And so we're going to call this a shallow likelihood. So the likelihood of my MLE, the likelihood function, L of theta here, is very shallow around my MLE. And what that means is that if being at the MLE is not much better than being over here or right over here. Technically, it is slightly better to be at the MLE, but I could be off the MLE a little bit, and it actually wouldn't decrease my likelihood that much. And if the principle is we want to choose the most likely value for theta as our estimate, then it's not going to matter a lot if we're slightly off it one way or slightly off the other way if we have a very shallow likelihood. My second possibility is, of course, if I have a very curved likelihood. Okay. And so my MLE is going to be something like here, and maybe that's what L of theta looks like. So here's my MLE. But in this case, if I'm slightly off of my MLE, so, if I were to guess slightly wrong, not guess my MLE, but pick a value slightly off of that MLE, my likelihood decreases by a lot. So this is a very, the opposite, curved, very curved MLE. And what that tells us is that if that the MLE is strongly preferred. So let me actually write this down. This is strongly preferred, right? It's strongly preferred to be at theta hat, to be at my MLE at theta hat, then slightly off of it. Because if I go slightly off of it, I end up with a much less likely value of theta hat. Whereas in my shallow case, I only weakly prefer my MLE over other estimators. Why? Because yeah, my MLE is technically the maximum value, but if I go slightly off it one way or the other, it's not actually that much better. It's not that much more likely to have been the true theta if I'm slightly off it. Whereas in the other case, if I go slightly off it, I am much less likely, according to my likelihood function, for that to be the right value of theta. So in the second case here, I strongly prefer in the curved. And one way we could measure this is look at the second derivative. If we look at the second derivative, if we have a shallow likelihood, dl d theta is going to be small around theta hat. And if we have a very curved likelihood, the second derivative is going to be very large around theta hat, MLE, because it's very curved, right? In both these cases, note that, and we'll come back to this, we saw this in one of our problems, that because we're maximizing this thing and it's concave down, right? So the second derivative is negative. That just means it's concave down and we're finding a maximum. That's okay. But in absolute value, let's say, it's small in absolute value. So the second derivative tells us something about how much we strongly or weakly prefer one value of for our MLE over another choice, or one value of theta over another. And somehow this second derivative is giving us information, or telling us about how much information our data has about the true value of theta. In the strongly curved case, we have a large second derivative, and it's telling us that we have a lot of information in our data about where theta should be, and so we strongly prefer one value over another because we have a lot of information that should be actually here at the MLE and not slightly off of it. In the weaker case, when we have the second derivative small, we don't have a lot of information. Our data does not contain a lot of information about the value of theta, and we don't really care if we're slightly off it one way or the other, because our second derivative is small, the information we have about our thing is small. And so we don't strongly prefer one over the other. Okay. So that's the kind of deterministic case. And as in the other case, let's look at a theorem. And this theorem has a couple parts. I think I can write it as one line. What we're going to say is that if I look at the variance of my score, the variance of my score is going to be the same thing as the expected value of the square of the score, which is the same thing as the negative of what I'm going to call, I'm going to write it like this, right? The negative of our second derivative of our likelihood function, but viewed randomly. So the same way that my score here is kind of this first derivative, right? You could instead take the second derivative, and instead of, so when we go back up to our exponential example way back up here, right? I said we had dLd theta, which is kind of deterministic, and we had the score, which basically replaces little xpens with big xn's, right? You could take another derivative. You could look at the second derivative, and you could, again, play the same game where you replace in this case, it's not super interesting, but one could. And you could view this thing as a random, but you could do a second derivative and replace the deterministic xpens with random sample. And so that's kind of what I'm calling the second derivative here. Okay, so let's take a minute and parse this out. So it has kind of three equalities. One of them is super simple. One of them takes a little bit more work, but none of it's too bad. So what this is saying is that, so we had, the first theorem was at the expected value of the score, and we said the expected value of the score is 0. And now we're going to say something about the variance of the score. We're going to tie this all back together by the end of the lecture. Okay. So this theorem says the variance of the score, so this is kind of equality 1, is equal to the expected value of the second, or the second moment of it. This is easy. So proof of 1 is that, note that the expected value of my score is 0, right? So, of course, we have our shortcut formula for the variance of my score is, the variance of the score is the expected value of the second moment minus the expected value squared, that's 0. And so we just get the variance is the expected value of the square. That's very straightforward. It just comes from the first part, the fact that the expectation is 0. We have the second more interesting equality here. And the second kind of more interesting one is that it gives us a way of calculating this variance of the score without needing to square it, right? Another way of viewing this is that if I, say that kind of in this abusive notation that the score is dLd theta squared, then the second equality says that score is dLd theta squared, viewed as a random quantity. If I look at the second moment of that, so I square it, that is the negative of the expected value of second derivative. Now, this is doing what we've always wanted to do in calculus. It's saying in certain circumstances we basically can do that, right? This is the square of the first derivative, view it as a random quantity, and this is the second derivative. Normally, the square of the first derivative is not the second derivative, right? You can't just push that 2 through, right? Oops, that should be a square there, right? You can't just do that. That's kind of a Calc 1 mistake. Turns out you can in this case. At least in expectation, you have to throw in a negative sign. Notice, but we'll talk about that, but you can basically, it says that instead of calculating the score, taking the derivative and then squaring the thing and then calculating this expectation, which might be hard, you could just take 2 derivatives, which is generally going to be much easier, and you can take the expected value of it. Notice again that this thing is bigger than 0. Right, this expectation of something squared. This thing we generally expect to be negative, but then we have a negative sign, so we get negative, negative gives us positive again, so the signs are all matched up. The interpretation is very similar to the first theorem we had, right? Which is that what this is telling us is something about the relation between the variance of the score and the concavity, the curvedness of the log likelihood function, right? We said that this curvedness tells us something about how much information, it seems, our data has about the unknown parameter theta. Does it strongly prefer some estimate at theta hat MLE, or does it only weakly prefer? And what it tells us is that the variance of this score function is somehow related to that concavity, at least in expectation. And so we're going to expect, and we will show, maybe this lecture, maybe next lecture, that this quantity tells us a lot about how much information our sample contains about our unknown parameter. So this is why this score function is so important. The score function in expectation is 0, because in expectation we should be getting our MLE should be telling us what the truth is, truth data. And the variance of the score is going to tell us something about how much information our data has. And it's going to tell us something about how accurate our estimate's going to be. Because the other way you can view this is that if we only weakly prefer the MLE over other possibilities, we're going to think maybe my MLE is not that accurate. But if we strongly prefer the MLE over other alternatives, we're saying, I believe my MLE is very accurate. We strongly prefer this. And so this is telling us this variance of the score, which is why we're kind of studying this weird kind of theoretical construct. The score tells us something about how much information, and therefore we're going to say how much how accurate our estimate is going to be. And of course, at the end of the day, we want to say something about the best estimates, and so we want to say how accurate we expect an estimator to be, and this is going to all tie into that. Before we move on, let's just prove this equality 2 here. So let's just prove this. It's, again, not too bad, and it's going to abuse an interchange between differentiation and integration again. So here's how the proof goes. 0. 0 is, of course, the derivative of 0 with respect to theta. That's not controversial. Derivative of 0 with respect to anything is 0. But we know a certain thing that is 0. Something that we're used to being, that we just showed is 0, is the score. So the expected value of the score is 0, right? So we can plug that in. And we can write what the score is, right? Or the expected value of the score, right? It's the integral of score, which is basically DLD theta, being multiplied by the PDF, and we're integrating against all of our little x's, and that's my notation for integrating against all my little x's. And, okay, now I'm going to abuse an interchange. I'm going to bring that derivative in, and I can now say, well, it's 2 first derivatives, or it's the second derivative. The second derivative, d squared LD theta squared, right? It's the derivative of dLD theta, okay, which we call the second derivative. And that's definitely not allowed, because that's cheating. Let's back up here. What am I doing? Let's try this again. Right? I'm taking the derivative of a product of 2 functions. I'd get points off in my calc test for this one. We're taking the derivative of a product, right? And that's the product of first derivative and some other function, right? And so the product rule says it's the derivative of the first times the second plus the first dLD theta times the derivative of the second. And all of that is in my integral, right? Let's just put a star here to denote that we need regularity for this proof to go through, as with last time. Works for exponential families, that's okay. And so let's just combine some things. This is, we have our integral, now we have d squared d theta squared, right? We multiply by f theta. And then we have the second part, which is dl d theta times the derivative of f with respect to theta. Now, if we go back up to our previous proof here, we're going to use this fact, which is that we said dl d theta can be written as the derivative of f with respect to theta over f. So let's place that in there. We, of course, get dl d theta. That's not changed. Oh, no, I'm sorry. That is what we're replacing, right? So this is derivative with respect to theta, d theta of that thing, over f theta of x, right? We claimed that was dl d theta. And then we multiply by right? Yes. Okay. You know what? This is, let's just, this is going to be easier. Let's rewrite this. Sorry. Let's rewrite this. Note from above, we had the fact that dl d theta was d theta f theta over f theta, right? And so we could rearrange that. This is going to be a simpler way of doing it, is that if we looked at d theta f theta, this will give us dl d theta f theta. Okay, so now we can actually replace that part. Let's replace the second part just to make our lives easier. And so we still have dl d theta, and then we replace this with another dl d theta and f theta. And okay, that is all in our integral. Good, good. And so let's just distribute this integration across. Okay, and this is dl d theta quantity squared. It's 2 copies of it. F theta of x dx. Okay, so if you recall from above, we had started off with 0, so we can actually bring this all the way down to here. This is all equal to 0. Notice that this first integral is, all right, we're viewing is exactly the expectation of the second derivative, d squared l d theta squared. And the second one is the expectation of the square of the first derivative, right? It's this thing times the PDF, and you integrate it. That's called expectation. So here, again, I'm abusing my notation a little bit. Normally, you know, dl d theta is the deterministic one, but we're viewing these kind of now as random quantities, okay? And so the sum of these things is equal to 0. So pick your favorite. Let's say the expected value of the square is negative. We can bring that to the other side of the expected value of that. And typically people might write this as the expected value of the square of the score is basically negative of the expected value of, let's say, if we look at, another way you'll see people write it is, oops, the second derivative of log f theta of x. Doesn't really matter which way you want to write it. These are all kind of equivalent ways, right? Because this is L of theta, it's the second derivative. Not a big deal. But so that's the proof. But if you look at the proof, it's actually just kind of rearranging and using some clever facts. It's not too complicated. It does involve this regularity, which is going to kind of interchange with differentiation and integration. That is okay for exponential families. Not going to work for families where the parameter, the underlying unknown parameter, changes the support. So the point of this theorem is that, so we proved it, which is that the variance of my score tells us something about kind of the negative, or ignore the negative, the absolute value of the concavity. So the variance of my score tells me something about how concave on average, this is the expected value of the second derivative of the log likelihood, kind of if I were sampled a bunch of stuff and I would throw it in my log likelihood, what's the kind of concavity I would get typically if I were to do that. The variance of my score tells me something about that. And we said that this concavity tells me something about how much information that I have about my parameter and kind of how much I prefer different estimates over others. So the proof is not something you need to memorize. The fact is, and we'll kind of conclude this lecture in the last several minutes here with codifying this whole thing into what's called the Fisher information, named after the preeminent English statistician, Ronald Fisher in any case. And it's basically just going to name the second derivative quantity. So we define, the Fisher information. I'm supposed to read Fisher. Man, I can't write Fisher information for a parameter theta. Do I want to preface this with anything? Let's think. Let me just start off by saying, if I have a single sample, some x that comes from some distribution f theta, in that case, we define the Fisher information for theta, let's say contained in my single sample x as, and we'll say I for information, I of theta. It is going to be negative of the expected value of d squared d theta squared of the log of this PDF evaluated at x. So this is basically a situation where I have n is equal to one sample. If I have one sample, we define the information contained in that sample for the parameter theta as basically this negative negative second derivative thing, right? And it's basically going to tell me about the concavity of, well, it's not really a log likelihood, it's only one sample, but it's like the negative, it's like the concavity or the expected value of the concavity of the log likelihood if I have one sample. If, let's immediately generalize this, if I have some capital N samples, my samples, these x sub n's, are from this distribution, then the Fisher information contained about theta in these n samples is, and we're going to call it I with a little subscript n, because we have n samples now of theta, so the n information of theta, And it turns out, and we're going to prove this, that it's just n times the amount of information I have in one sample. The reason for that is we have independent samples, and their information is just going to add together. So this is formally codifying what we're calling information about a parameter. So to have a single sample, I have this much information about my parameter theta. And if I have n samples, I'm going to have n times that amount of information. And this information, of course, is this kind of second derivative, kind of related to the second derivative of the log likelihood. And so it tells me about how much information I have about my parameter, and that's going to tell me how much I prefer some estimates over the other, how accurate I know those estimates are. It tells me about what I know, how accurately I know something about theta, which is going to tell me how much I prefer one of these estimates over the other. We can actually prove this fact. So I claimed that because if I have independent samples, their information just adds. People probably will believe that, but you can actually prove it, and it's not so bad, right? If I add of theta is, we could define it as, in a similar way, but instead of just, in the one case, we just had f of 1x. Now we have a bunch of x's, right? So we have a bunch of these things instead of just one. Of course, we know that the joint distribution, because these things are independent, oops, I'm missing a squared there. This is log, and they're independent, so this is just a product of my marginals, my x sub n's, right? And if I look at the log of a product, that is just going to be the sum of the logs, right? That's just rules of exponentials. I'm sorry, rules of logs of products. And everything here is linear. Expectation is linear, and so is differentiation. So I can pull that sum all the way out. This is the sum up to n of negative the expected value t squared the theta squared of log. And this is just the information. This is just the information contained in H, info in each. And they all have the same distribution, so they all have I of theta information, and we sum it up n times, we get n I of thetas. So that's where they come from. Independence there gives us the fact that that they are that we can just add up the information. So that's pretty nice. So before we kind of totally go abstract here, because this has been a little heavy proof-based for this lecture. Unfortunately, you can't avoid it. Let's look at one example, and we'll end on this example. So our example maybe is, let's have data from a Poisson distribution, right? So this means what? That f lambda of x is lambda to the x e to the negative lambda over x factorial. L of lambda, or no, we need to call it. If I look at the log of f lambda of x, it's going to be, what is it? It's x log lambda minus lambda minus log of x factorial. And so this is an example where we're going to calculate the Fisher information. How much information is contained in my sample? Now, you notice I'm working with just one, because we know if I calculate the information contained in one of my samples, it's just n times for n samples. So you can always do these calculations basically with one sample and then multiply by n. So super easy. And what I said is I look at log, the log of the PDF, take two derivatives with respect to the parameter, and then I take the expected value. I kind of treat it as random, take the expected value, throw on a negative sign. So that's what I'm going to do. So let me say 1 is find log f theta, let's call it, generically. 2 is find two derivatives of this, d squared d theta squared of log f theta. Right, so you can see why at the beginning of the lecture I said you got to keep careful what's random, what's not, right? Because here we're kind of viewing as we're not plugging in the random variable into its own PDF, but we will. The second step is you find the second derivative, right? So d squared d lambda squared in this case, log f lambda, is, so that's just two derivatives of this bad boy, right? Let's do this one step at a time. First derivative is what? X over lambda minus 1. The log of x factorial goes away. Super cool. And that means, so that's the first. The second one is what? It's, well, the negative 1 goes away and it just becomes 1 over lambda. No, we're taking derivative with respect to lambda, right? So it's negative x over lambda squared, right? And so 3 would be to, let's say, let's write it this way, find, right? So here's where, again, a lot of confusion crops up, right? So this thing uses this little x, it's deterministic, we view it as some little value. Now we're going to replace little x with a random variable. So we're going to find, so there's different ways of denoting it. Sometimes I've called it d squared ld theta squared when I'm lazy, or you could, and kind of more formally, first we want to find the negative, more formally in textbooks they tend to just write it as d squared d theta squared log of f theta of x. So now this is, x, capital X, so it's random. So we're basically, right, so in this one, like little x is not random, but we're plugging in the random now, which means we can actually take an expected value of it. That makes sense to talk about. And so we want negative expected value of this thing, which would be negative, but instead of little x, we have capital X. And of course, negative cancels. We can pull the 1 over lambda out, and you get 1 over lambda squared, expected value of x. So that's 1 over lambda squared. And x is Poisson, so that's just lambda. So we get 1 over lambda. And if you want, your fourth step is that so this is equal to the information contained in one sample. If we want our n sample version, all we do is we say in of lambda is n times whatever that is. In this case, it's n over lambda. And that's basically our answer. So this is the information contained in one sample. And if we have n samples, it's n times as much information. And we'll see what we can do with this information next time. But for now, we're just going to be satisfied and say this is a measure of how much information we have about lambda in our sample. We call this the Fisher information, and it is a very kind of central quantity. This whole conversation is very central to the rest of the course. So this is the kind of stuff that we're going to be talking about. It'll get a little more practical, yeah, so that's Fisher information, which is a really important quantity in this whole field of mathematical statistics. But I'll leave it there. And next time we'll pick up here and we'll figure out how the amount of information we have relates to how good my best estimator is.